In the last video, we defined the differentiability of a function f from Rn to R. Recall that differentiability depended on the existence of an A that satisfies some special conditions. However, it was not clear to us how to determine this A. In this video, we will come up with an algorithm to find this A. A slight reformulation of the above definition will come in handy in this process. Notice that if we denote x minus c by h, then x is equal to x minus c plus c, which is equal to h plus c, or in other words c plus h. Also notice that x tends to c is equivalent to h tends to 0. Therefore, f of x is equal to f of c plus h minus f of c minus a dot x minus c, which is equal to h whole divided by norm of h. And limit x tends to c is same as limit h tends to 0. Therefore, the above limit can be restated in this manner. Thus, we can say that a function f from Rn to R is differentiable if there exists an A in Rn such that limit h tends to 0, f of c plus h minus f of c minus a dot h whole divided by norm h is equal to 0. And now the key idea to determine C is to see what happens when we approach C along a line. More precisely, let us fix a point x in Rn. Then notice that as epsilon tends to 0, epsilon x also tends to 0. And here by 0, I mean the origin. Therefore, we can consider limit epsilon tends to 0, f of c plus epsilon x minus f of c minus a dot epsilon x whole divided by norm of epsilon x. Notice that we replaced epsilon x tends to 0 by epsilon tends to 0 because they are both equivalent. And as f is differentiable at the point C, we know that this limit has to be equal to 0. Further notice that norm of epsilon x divided by epsilon is equal to mod epsilon by epsilon into norm x. Now notice that mod epsilon by epsilon is either plus 1 or minus 1 and norm x is a fixed number. Therefore, this product is bounded. As this product is bounded and this converges to 0 as epsilon tends to 0, we know that their product will also converge to 0 as epsilon tends to 0. In other words, we know that limit epsilon tends to 0, f of c plus epsilon x minus f of c minus a dot epsilon x divided by mod epsilon times norm x into mod epsilon times norm x divided by epsilon is also equal to 0. Notice that we can cancel off mod epsilon times norm x, and also notice that a dot epsilon x is equal to epsilon times a dot x. Thus, we can write that limit epsilon tends to 0, f of c plus epsilon x minus f of c by epsilon minus a dot x is equal to 0, which can be further simplified as follows. Now observe that if you take x is equal to ei, then a dot x is equal to a dot ei, which is equal to ai. Therefore, if we evaluate this limit for all the ai's, we will be able to find a. And also observe that this limit is in some sense very similar to what we have done for functions from R to R. Because here the only thing that varies is epsilon. So it's in some sense a one-dimensional limit that we are taking. Let us summarize the discussion so far in the form of some definitions. We will call limit epsilon tends to 0 f of c plus epsilon x minus f of c by epsilon as the directional derivative of f at c along the direction x, and it is denoted as df of c comma x. Let us repeat. It is called the directional derivative of f at the point C along the direction x. We saw that the directional derivative along the vectors in the standard basis help us find the derivative if it exists. Therefore, these quantities have special importance, hence they have a name. They are called partial derivatives. And sometimes we use simpler notations for these quantities. Two alternative symbols that are used for partial derivatives are either del f by del xi at c or dif at c. And we saw that these form the components of the derivative if it exists. More precisely, if f is differentiable at the point c, then the derivative of f at c is given by del f by del x1 at c, comma del f by del x2 at c, etc. up to del f by del xn at c. And this vector is called the gradient of f at the point c. And it is denoted as nabla f of c. You can read it as nabla f of c or gradient of f at c. I had casually remarked earlier that these directional derivatives, or in other words these limits, are one-dimensional in nature. Let me make this remark more precise. Let the setup be as before. That is, f is a function from Rn to R and c and x are points in Rn. Given this setup, we can define a function capital F from R to R as follows. We define capital F of epsilon to be equal to small f of c plus epsilon x. Notice that as f is a function from Rn to R, f of c plus epsilon x is an element in R, and the input is also a real number. So capital F is a function from R to R. Now notice that the derivative of f at the point 0 is equal to the directional derivative of small f at the point C along the direction x. And this is exactly what I meant when I said that the directional derivatives are in some sense one-dimensional limit. Another way of understanding capital F is as follows. Given the points C and x, I can define a curve, or in other words a function from R to Rn as follows. I define gamma of epsilon is equal to c plus epsilon x. As c and x are elements in Rn, c plus epsilon x is also an element in Rn. So this is a function from R to Rn. Notice that capital F is equal to small f composed with gamma. So this is another way of understanding that f is a function from R to R. And with the help of these ideas, we should be able to make more sense of directional derivatives now. Let this point be C and this point be X. Then notice that the image of gamma is the line that passes through C and X. And the directional derivative of f at the point C along the direction X is the derivative of the function that you obtain when you restrict it to this line. That is the basic idea behind directional derivatives. So the partial derivatives are derivatives when we restrict our attention to the different axes. And the basic lesson or takeaway from all this is the following. Given a multi-dimensional question, we can convert it to a single dimensional question by restricting our attention to a curve. And the answer to this single dimensional question can inform us a lot about the multi-dimensional question. Of course, the answer might not be complete, but we still learn a lot from it. And this idea will be repeated many times throughout this course.